So here is our uniform rod. Since we're dealing with essentially one dimension here, we will be considering the mass per unit length of the rod. So it's a thin rod, so we can ignore its thickness. Here we have a uniform thin rod, so we're ignoring its thickness. So we're only dealing with one dimension essentially here. It's a good approximation anyway. So since it's uniform, its mass per unit length will be constant. So we're dealing with mass per unit length here, and we will call that rho. So rho is mass per unit length. So again, it's a bit like a density, but a density is in general mass per unit volume. So here the units will be kilograms per meter. Well, at least these would be the SI unit. So we're going to take a small mass element, whose mass is delta m, of course, and we're going to consider its distance from the axis of rotation. Well, I've just lined up along an x-axis, so we'll call its distance from the axis of rotation x, at least the distance of this end of the mass element. But of course, in the limit, as delta m becomes very, very small, this line here will coincide with this line. Since we're dealing with lengths here, we will get delta m in terms of its length. So we'll call its length delta x. That's no surprise. This is just a change in x. So this will be delta x. So we see that delta m is going to be the length of the mass element, delta x, multiplied by its mass per unit length, which is rho. Again, this makes sense. Delta x has units of meters, rho has units of kilograms per meter. So the m's go out, so we're left with units of kilogram. That's what we want for the mass element. So if rho is the mass of 1 unit of length, then delta x units of length will have mass delta x times rho. So this rod has a length of L, so the coordinates of this point are L. Let's get the moment of inertia of this mass element. So what do? We multiply its mass by the distance squared of it to the axis of rotation, which is this dotted line here. So that distance is x, so we have to square x. So we want to sum the moment of inertia of all such mass elements from x equals 0 to x equals L. That'll give us an approximation to the moment of inertia of the rod about this axis here. That approximation becomes exact, of course, if we let delta x go to 0. That's the length of each element. Then this limit of a sum becomes an integral. We're integrating from 0 to L. The rho is just a constant. I can take it out. We have x squared, and we write dx for delta x. So the length of each mass element is delta x, and to make the approximation exact, we let delta x go to 0, and we write dx for delta x. So we're integrating x squared with respect to x. That's a straightforward integral. We get 1/3 x cubed. So our final answer then is going to be rho L cubed over 3. Now let's get this in terms of m. M is the mass of the rod. Rho is the mass per unit length. So to get the mass of the rod, we multiply the mass of 1 unit of length by the length of the rod, which is L. So again, this has units kilograms per meter, this is units of meters, so we'll end up with kilograms per meter times meter. The m's cancel to get the mass in kilograms. So we can factorize rho L out of this here, and if we do that, we'll have rho L times L squared over 3. And we can replace the rho L with m. So our answer is ml squared over 3. So we have the moment of inertia of a rod about one of its ends, but of course if we do that calculation about some other point, we'll get a different answer actually. Next we will do the calculation about the center of the rod. So we imagine trying to rotate the rod about an axis going through the center, perpendicular to the rod. And we will compare the two answers. We'll compare it to this. Okay, our origin now is at the center of the rod, And let's take a mass element over here somewhere. So this is our delta m. The length of this mass element is delta x because the mass of the element depends on the length. That's the only dimension that the mass depends on. We're assuming that we have a thin rod. The distance of the mass from the origin is x. Well, the coordinate is x, but we don't have to worry about that too much because we'll be squaring this quantity. So whether x is positive or negative, when we take the square, it'll be positive. For elements on this side, of course, x will be negative. Okay, we'll have negative x. Okay, let's look at this element here. Now, just like before, we know how to get delta m. Since rho is the mass of a unit length, then a mass with a length of delta x will have a mass of rho times delta x. The moment of inertia of it is x squared times delta m, x squared times the mass element, or x squared rho delta x, just like before. So to get the moment of inertia of the entire rod, we have to sum all such moments of inertia. Now, the rod has a length of L. So since our x-axis has its origin at the center of the rod, this point here has x coordinate minus L over 2, and this point has x coordinate plus L over 2. So we're summing from x equals minus L over 2 to x equals plus L over 2. So this is the difference from the previous example. In the previous example we were summing from 0 to L. Now again, as I said before, we don't have to worry about x being negative for mass elements at this end of the rod because we'll be squaring the coordinate. So we will still end up with the distance squared. It'll come out to be positive. X squared will be positive. So like we start off with a mass element right at the very end of length delta x. That would be the one at minus L over 2, and then we get its moment of inertia about this axis here. Then we take the next one and so on all the way through 0, and then all the way out to x equals plus L over 2. This will be the last one. So again, this is only an approximation because delta x is not small enough yet. So we're getting the distance of the mass element, you know, is the distance to this part of the mass element. So to make the approximation exact, we need to make delta x go to 0. So we take our limit to make the approximation exact, and the limit of this sum becomes an integral from minus L over 2 to plus L over 2. Delta x becomes dx like we saw before. So it's the same integral as before, just has different limits. So let's plug in these limits. So we're going to have L cubed over 8 on top. So we have minus L over 2 cubed here. So we're going to get a plus here. So we're going to get 2 of these terms on top. 2 rho L cubed over 8 all over 3. So we're going to end up with rho L cubed over 4 all over 3. Well, that's going to give us rho L cubed over 12. Now, as before, we know the mass of the rod is the mass per unit length times the length of the rod. That's rho L. So we can factorize rho L out of this, and we end up getting ml squared over 12. So, as you can see, we get a different answer for the moment of inertia of the rod about the center of the rod. We actually get a much smaller answer. ml squared over 12 is much smaller than ml squared over 3. As a matter of fact, this is a quarter of this here. So that tells us that the effort required to turn the rod about this axis through 0 is 4 times less than for the turning effect of the rod about the end of the rod, one of the ends of the rod. And that sort of makes sense if you think about it, because when we're calculating moments of inertia about the center of the rod, the mass elements are closer to the center. So you see a mass element here is only L over 2 away from the center. So, and we're multiplying that mass element by its distance squared. Whereas when we're getting the moment of inertia about the end of the rod, we have to consider mass elements that are further away, like this mass element is now a distance L away from this. So we're getting the square of that distance. So it's not surprising that this number is bigger.